This video covers section 2.2 on properties of matrix operations. In this section, we'll go into more detail on how to calculate with matrices and also how to do algebra with variables that represent matrices. So unlike when dealing with real numbers, matrix multiplication is not commutative. So you have to be careful when multiplying matrices together. But mostly the other properties follow as we're used to. So theorem 2.1 here discusses the various different properties of matrix addition and scalar multiplication. You can see that in terms of these operations, the properties that you're familiar with, commutative property of addition, associative property of addition, associative property of scalar multiplication, the multiplicative identity, where if you take the scalar multiple of 1, it doesn't do anything to the matrix, and the distributive property of scalar multiplication. So these properties we're already familiar with, and they carry over to matrix addition and scalar multiplication. So basically, these operations behave as you're used to with real numbers. So the associative property here essentially says that when you're adding more than two matrices together, you can just add them in any order. So here, when adding three matrices together, you can do the addition all at once, right? So negative 7 plus 8 is positive 1, and then minus 2 gives you a negative 1. Then 3 plus 4 is 7, then minus 5 is equal to 2. Okay, so again, matrix addition and scalar multiplication isn't really any different than what you're familiar with when dealing with real numbers. So on the bottom of this page, we have a short discussion of the zero matrix. So the zero matrix of size m by n is just a matrix with zeros in every single entry. Right, so here's the 2 by 3 matrix, the 2 by 3 zero matrix. So again, the zero matrix plays the same role as adding by zero does when working with real numbers. Right, so any matrix plus the zero matrix doesn't change the matrix. And if you subtract a matrix from itself, it cancels out and you get the zero matrix. And if you have a number a scalar times a matrix and it's equal to the zero matrix, either the scalar multiple was 0 or the matrix itself has to be the zero matrix. So again, this behavior is similar to what we're already used to. Since the operations of scalar multiplication and matrix addition behave basically the same as what we're used to with real numbers, we can solve linear equations involving these two operations, again similar to what we're used to when dealing with real numbers. Right, so here in this example, you're given some known matrices A and B, and some unknown 2 by 2 matrix X, and this is a linear equation with one unknown matrix. And if I want to solve this matrix equation for X, it only involves matrix addition and scalar multiplication, and so we can solve the equation exactly as we're used to. Right, so we want to get the X by itself. So first we cancel A by subtracting A from both sides. Right, so that'll cancel this a out. And what's left is minus 2x on the left is equal to b minus a. And then now I need to cancel the constant multiple by taking the multiplicative inverse, which is the reciprocal, minus 1/2. So I multiply both sides by minus 1/2. To cancel the constant multiple. And then, so this cancels out, and now the x is by itself. So we get x is equal to minus 1/2 times the quantity b minus a. And we know what b and a are, so we can just calculate. So b is the 2 by 2 matrix, -5, 1, -2, 7. And a is the 2 by 2 matrix, 2, 4, -3, 1. And then now we can do the matrix calculation. So first the subtraction. So -5 minus 2 is -7. 1 minus 4 is -3. -2 minus a -3 is -2 plus 3, which gives you 1. And 7 minus 1 gives you 6. And then the whole thing is multiplied by -1/2. So we get 7/2. This entry will be 3/2. This will be -1/2. And this will be -3. And that's our matrix X. Okay. So again, basically the procedure here is what we're used to when solving linear equations. Okay, so now let's take a look at the properties of matrix multiplication. So again, some of these properties you're familiar with. So the associative property says when multiplying 3 or more matrices, it doesn't matter which order you multiply them in. And it also has the distributive property, both from the left and from the right. So here you have to distinguish multiplying from the left and multiplying from the right, because as you can see, the commutative property is not part of matrix multiplication. Right, so we've already seen that matrix multiplication is not commutative. So, well, we'll see in a second an example where it's not commutative. But before we do that, let's take a look at the associative property. Right, so again, it says that when multiplying 2 or more matrices, they don't all have to be the same size. They don't all have to be square matrices. They can be differing sizes as long as the rule where the columns and rows matches up. Right, so this is a 2 by 3. This is a 3 by 2. This is a 2 by 2. Right, so notice the 2 matches the 2 here, and the 3 matches the 3 here. So the number of columns and number of rows matches up the way we need for the multiplication. And we will see that whether you do this multiplication first or this multiplication first, the result is the same in both cases. Right, so let's do this multiplication first. So this matrix stays the same. Right, so it's 1, -5, 0, -2, 3, 3. And then this will produce a 3 by 2 matrix. Okay, so now let's do the multiplication. This is 12 plus 4 is 16. Negative 6 minus 12 is negative 18. 0 plus 1 is 1. 0 minus 3 is negative 3. 4 plus 1 is 5. And negative 2 minus 3 is negative 5. Okay, so now let's multiply these two things together. So this is 2 by 3, 3 by 2. Okay, so it produces a 2 by 2 matrix. And what are the entries? It's 16 minus 5 is 11, plus 0 is 11. Negative 18 plus 15 is negative 3, plus 0 is negative 3. This is negative 32, plus 3 is negative 29, plus 15 is negative 14. 36 minus 9 is 27, minus 15 is 36, minus 9 is 27, 27 minus 15 is 12. Okay, so this is the 2 by 2 matrix we get, and now let's check our result by doing the multiplication in the other order. Right, so first 2 by 3 and 3 by 2 here, so that will give me a 2 by 2 matrix. So what is this? Negative 3 plus 0 plus 0 is negative 3. Then 4 minus 5 is negative 1. Then 6 plus 0 is 6. Minus 3 is negative 3. And then negative 8 plus 3 is negative 5. Plus 3 is negative 2. Okay, so that's this multiplication. Then this one stays the same. So multiplying these, you get 12. 12 minus 1 is 11. Negative 6 plus 3 is negative 3. 12 minus 2 12 minus 2 is positive 10. Negative 6 plus 6 is 0. Okay, so this bottom row doesn't match up. Maybe I've made a mistake somewhere. So let's go back and check. So this is positive 6 minus 3, so that's a positive 3. So this should have been a positive 3. And let's say this entry was this times this, so that's negative 12 plus 3 plus 3 is negative 12 plus 6. Okay, so that should be a negative 6 here. Let me now erase it, just cross out. So this should have been a negative 6. Okay, so now let's multiply this again. So negative 12 negative 8 plus, this was negative, Negative 2 times 8, 4 is negative 8. Plus 3 plus 3 is negative. Okay, so this was correct the first time, negative 2. Okay. So now let's multiply these. So negative 12 minus 2 is negative 14. And then 6 plus 6 is 12. And we see that these two are the same. Okay, so you can see that, again, when multiplying a bunch of matrices together, the order doesn't matter. So the intermediate calculation might look different, but the end result still results in the same matrix. Okay, so as we said, in general, matrix multiplication is not commutative, right? So as an example here, we have these two matrices A and B, right? So we'll multiply them in both orders, A times B and also B times A, and we'll see that the result is not the same. So first A times B, so what do we get? It's 2 by 2 and 2 by 2, so the result is 2 by 2. Okay, so we get negative 2 minus 3 is negative 5. 4 minus 3 is 1. 2 plus 2 is 4. Negative 4 plus 2 is negative 2. Okay, so that's A times B. Now let's try B times A. So now in the reverse order. So negative 2 minus 4 is negative 6. 6 plus 8 is 14. 1 minus 1 is 0. And negative 3 plus 2 is negative 1. So you can see that these two are not the same. So that doesn't necessarily mean that it's impossible for two matrices to commute, right? Because there are some matrices that do commute, like the identity matrix, right? So if I take the identity matrix and I multiply on the left by A, you get A, and if you multiply on the right by A, you also get A, right? So the identity matrix commutes with everything. But again, in general, matrix multiplication is not commutative. So what that means is, in terms of doing algebra involving matrices, when you have matrix multiplication involved, is you should always keep track of what's on the left and what's on the right, right? So here A is on the left, B is on the right. Here B is on the left, A is on the right. So as an example, so you can see here we have A plus B times A minus B, two binomials involving matrices, right? So as we know from algebra, if we want to multiply this out, you FOIL. The method is called foiling, right? So first, outer, inner, and then last, and you multiply these different combinations together, right? So first is A times A, and then outer is this one here. A is on the left, B is on the right, so that's A times B. And it's minus, right? Because this is positive, this is minus, so that's a minus. A times B, and 3 is B times positive A, So B is on the left and A is on the right, so that's plus B times A. And then fourth is the last, so B times B. So minus B times B. So A times A, we can just say is A squared. However, AB and BA are not the same, right? So as where we saw here, so you cannot put these two things together, right? So we just write as AB plus BA minus B squared, right? So again, these are not the same, so they don't cancel. So you might remember if these were not matrices and just regular real numbers, then this gives you a difference of squares, just A squared minus B squared, right? But if here we're dealing with non-commutative matrices, you can see that you do not get a difference of squares. So always be careful when dealing with matrix multiplication. However, one thing that does carry over is as long as you're multiplying the same matrix, same square matrix by itself many times, this is you can say that it's the same as raising to that matrix to a certain power, how many times you're multiplying by itself, right? So as you saw here, I can say that A times A is A squared and B times B is B squared. Okay. And then on the bottom of this page, we introduce the identity matrix, which plays the role of the number 1 when dealing with matrices, right? So the identity matrix is a square matrix, and you have a square matrix for each size, right? So the 1 by 1 square matrix is just the 1 by 1 identity matrix is just the number 1. The 2 by 2 matrix, the 2 by 2 identity matrix has 1s along the diagonal and 0s everywhere else. The 3 by 3 matrix again has 1s along the diagonals and 0 everywhere else in general, right? So this is called the main diagonal, which I've highlighted here. And in general, the n by n identity matrix has all 1s along the main diagonal and 0s in every other entry. And again, as I said, the identity matrix plays the role of multiplying by 1, right? So whether you multiply on the left or on the right by the appropriate identity matrix, it doesn't change the matrix at all. So you can see, say if I take the 2 by 2 matrix, identity matrix, and say I multiply this matrix here, 1, negative 3, negative 1, 2. Right, so this gives you 1 in this entry, and then this row times this column gives you a negative 3. And then this row times this column gives you a negative 1. And this row times this column gives you a negative 2. A positive 2, right, because it's 0 plus 2. And so the matrix stays the same. Here we introduce a new operation for matrices called the transpose of a matrix. So basically, if A is an m by n matrix, the transpose of A, which we'll denote by A with a capital T in the subscript, in the superscript, is basically formed by taking each row of A and turning it into a column for A transpose. And we'll see that if A is m by n, then A transpose turns into an n by m matrix. Okay, so for example, in this matrix here, because I'm starting with the 3 by 2 matrix. So this first row, which consists of 2 and negative 3, turns into a column, 2 and negative 3. The second row, negative 1 and 4, turns into the second column, negative 1 and 4. The third row, 7 and 5, turns into a column with 7 and 5. Right, so each row turns into each column in the transpose, and as you can see, the resulting matrix now is a 2 by 3 matrix. So basically, rows turned into columns for the transpose. Another way of actually seeing it is also, the reverse is true, right? So the columns for A turn into the rows for A transpose, right? You can see this column, 2, negative 1, 7, turns into this row, 2, negative 1, 7. And this column, negative 3, 4, 5, turns into this row, negative 3, 4, 5. So you can either think of it as rows turning into columns, or also columns turning into rows. Okay, so in this box here, they just discuss some properties of the transpose. Right, so if you take the transpose of a matrix, and then take the transpose of the result of that, right, so A transpose transpose, basically gives you back the original matrix. And this comes about because, again, for A transpose, rows turn into columns, but then if you take the transpose again, the columns will turn back into rows. So you get the original matrix back. Property 2 just says that the transpose of a sum is the same as the sum of the transposes. So you can distribute, in a sense, the transpose over a sum. And then the transpose is scalar multiple. That's pretty straightforward. And then the transpose of the product, this one you have to be a little bit careful about. So if you take the transpose of product AB, it is the product of the transpose, but the order reverses, right? So here, if you multiply first and then take the transpose, you have A on the left and B on the right. And here, if you take the individual transposes first and then multiply, now the B is on the left and the A is on the right. So in a sense, distributing the transpose reverses the order of the product, right? So, and this also applies for longer products, right? So if I do have A times B times C and then take the transpose, is the same as doing C transpose times B transpose times A transpose, again, where the order of the individual matrices has reversed order. So be careful about the product of things, as usual with matrices. And at the bottom of this page, we have two special kinds of matrices called symmetric and skew symmetric. So the definition of a symmetric matrix is one where A transpose is equal to A, and the definition of a skew symmetric matrix is if A transpose is equal to minus A. So because it's defined in this way, in both cases A has to be a square matrix. But instead of calculating the transpose of a matrix and then checking, you can see directly by the individual entries of the matrix whether it's skew symmetric or symmetric or neither, by just looking at what the entries look like, as we see on the next page. So in this first example here, I have a symmetric matrix. Right, so here you can see that a symmetric matrix, so these are 3x3 matrices, but in general, you can have larger matrices as long as these properties apply, right? So for a symmetric matrix, you can have any values along the diagonal, along the main diagonal. However, off of the entries off of the diagonal, the corresponding entries should match, right? So this entry corresponds to this entry corresponds with this entry, and this entry corresponds with this entry. Right, so they should, above and below the diagonal, they should match. So this and this matches, this and this matches, and this matches. And so if you have a matrix that looks like this, it'll be symmetric. And for a skew symmetric matrix, is a little bit different, right? So a skew symmetric matrix, so along the diagonal, you should always have all zeros for skew symmetric, and then off diagonal, again, they match up, but they should be negatives of each other, right? So so here you see this is a +5, so here it has to be a -5. Here is a -3, so here has to be a +3. Here is a -4, so here has to be a +4. Right, so corresponding entries off of the diagonal are opposite to each other. And so if you have a matrix like this, it's considered skew symmetric.